Hi, I'm the Science Samurai. I'm glad to have you here with me today. I'm going to show you today how to make your own boomerang, how to throw it, and even how to understand the physics of a boomerang. Now I hope today you have with you the equipment necessary to make your own boomerang. You will first need some cardboard, either in the form of postcards or boxes, a ruler, a pencil, a pair of scissors, a protractor, and a stapler. Now there's only one criterion for a good boomerang. It must come back to you. Okay, how do we make our boomerang? First, the easiest way is to use a postcard because it has all the right dimensions. You need 3 strips about this long. So use your ruler and measure the width of the postcard and divide it into 3 pieces, 3 equal pieces. So I'm going to make some markings on my postcard and use the pencil to draw lines down the length of the postcard to get my 3 pieces. So I'll get the scissors, cut along the lines. So I'll have 3 equal strips of cardboard. You want to do this as accurately as you can. The next thing you need to do is put the 3 pieces together. So you put your 3 pieces together like this, and use the scissors and cut the slit through the middle of all the pieces. You just want to cut a short slit, like this. Okay, you see the slit is about 2 centimeters long. And with this slit, you can then proceed to fit the pieces together, like this. The third piece is a bit tricky, in that you have to go under this piece and get the other slit, the other arm to come out on top of this other piece. So you have a very symmetrical setup after that. The next thing to make sure is that the angles between the arms are all equal. So for this, you will need a protractor. If we want 3 equal angles, we will need to get the angle up to 120 degrees. So I do this for one of the angles, hold it carefully, go to the next one, do the same, and the third one should be 120. Then you get a stapler and staple the pieces together. One staple like this actually holds the 3 pieces together, but I like to put a bit more just to make sure that the boomerang is stable. There you have it. Now it's time to test the boomerang. There you have it. So now I'll leave you some time to construct your own boomerang with your teacher, and you please feel free to replay this video if necessary. Good to see all of you ready with your boomerangs. Now, we're going to learn how to throw a boomerang. Okay, first thing, you hold a boomerang vertically and hold it between your fingers like this, between your thumb and fingers like this. Hold it at the end of one blade. Okay, and if it's a bit flexible, let it flop slightly inwards, right, towards your body. So if you're holding it in your left hand, you let it flop this way as well. Okay, when you throw the boomerang, it's important to have a wrist action. So you want to make the boomerang spin. Okay, you want the boomerang to spin this way, spin forward. Okay, you want the boomerang to spin this way. So the next thing for you to do is really practice, but just look how I do it. Right, observe again. And if you do it right, and your boomerang is good, it should come back to you. Now some questions for you to think about and to experiment with, really have fun with this. Instead of making it turn left, could you make it turn right instead? Do you think you can change the turning circle? Meaning to say, can you make the boomerang go further before coming back? Or do a smaller circle when it comes back? What do you think will happen if you throw your boomerang like a frisbee? If you throw it in this manner? Can you compare and contrast the performance of your friends' boomerangs? I'm sure they have different flight characteristics. Try to pin down what do you think is making them different. Notice how you must do a quick flick of the wrist. Welcome back. I'm sure you all had fun throwing your boomerangs. Now, you must be wondering what makes a boomerang come back. you have noticed there are a lot of factors that affect how a boomerang flies. It could be the stiffness of the cardboard, the type of cardboard you use, the mass of the cardboard, the width and the length of the blades. You would have some guesses as to how some of these factors affect the flight of a boomerang. Science is really about that. The process of making guesses, testing and explaining how the world works. And that involves observations. Now, did any of you try throwing a boomerang without it spinning? I don't think that would have worked. Now, when a boomerang spins, that's really very essential to what we call the precession of angular momentum. And that is actually the concept that allows the boomerang to come back to you in a circle. For this, let me try to explain it on the board, because you need some equations to understand how this works. So a boomerang looks something like this, right? Before we talk about the physics of a boomerang, there's this thing called the moment of inertia. Now, moment of inertia is a concept of how easy or difficult it is to spin something. Take this sword for instance. When I want to spin the sword around the long end, it's relatively simple, right? I can just spin it quite easily. But if I wanted to spin it this way, there's much more resistance to the motion, right? It's not so easy to spin the sword this way. It takes more effort, it takes more strength. Likewise, the boomerang has a moment of inertia. Now, we say that the sword has a low moment of inertia when it's spinning this way, right? Because it's easy, so the moment of inertia is low. And it has a higher moment of inertia when I spin it this way. So there's a certain moment of inertia associated with the boomerang when it spins this way. We normally call that I. Okay? We use I to symbolize the moment of inertia. And there's this formula, L equals I omega. This is a critical formula for the boomerang. Now, L is the angular momentum. If you know what momentum means, angular momentum is actually how much momentum it has in the spinning sense of the word. Omega here, instead of the, it's actually the angular velocity. And finally, I is your moment of inertia. Okay, we can take this as a definition. This is a definition of what angular momentum means. It means the moment of inertia multiplied by omega, the angular velocity. And angular velocity is basically how fast something is spinning, right? How many angles per second. You would have noticed that I drew these little arrows on top of L and omega. This is because these are vector quantities. So when the boomerang is spinning this way, the direction of the vector, we use the right hand grip rule. Okay, it's just a sign convention, meaning to say you put your fingers in the direction of the spinning, and the direction that your thumb is pointing is actually the direction of the vector. So in this case, omega and L, both of them, are actually pointing out of the paper. Okay, like this. So use your right hand to grip the direction. Now we have to make a comparison with Newton's laws. Most of you will know that Newton's law says that F equals m times a, where F is the force and a is the acceleration. Another way of writing this, which we'll do, is write this m times a as dp dt, the rate of change of momentum. In this case, P, what we call the momentum, right? And you have m here, the mass, which is also called inertia. So notice the similarity. This is the moment of inertia, this is the inertia. And v is actually the velocity. So we see that F equals to dp dt, where P equals to mv. This P, momentum, is mass times velocity. Angular momentum is moment of inertia times angular velocity. So very similar to Newton's second law, we have that there's this thing called the torque, tau. The symbol is tau. equals to dl dt. Okay, I hope you can see the similarity there. This tau, the top, is behaving like a force. Okay, the torque actually means the turning effect of forces. So these are the two main equations that I've introduced now. The four main quantities: moment of inertia, angular velocity, angular momentum, and torque. Okay? And these three are vector quantities. I'll give you some time now with your teacher to clarify any questions you have about all these things that I've introduced. But when you come back, I want you to tell me what happens to the angular momentum L if I have a constant omega. That means I keep the angular velocity the same, but I increase I. I want you to think about that, and we'll come back after the break to finish up the explanation of the boomerang. Welcome back. I hope by now you have some familiarity with concepts of torque and angular momentum. Now, regarding the question I asked you at the end of the previous segment, what happens to L when I increases and omega is constant? I believe you can see from equation 1 that L is actually proportional to I, which means that if we keep the angular velocity the same and we increase the moment of inertia, the angular momentum should increase proportionally. Now I'm going to use this segment to wrap up the discussion and really put together the pieces of the puzzle that we have to solve. Right? How the boomerang comes back to you. I'll begin by drawing something. Give you a hint. This is my nose. This is my hand. And this is the boomerang. Okay, so we're now doing a top view. Okay, in a top view, remember when I throw the boomerang like this, it actually spins this way. So if you imagine you're looking from the top, right? You're looking from the top. When I throw the boomerang like this, what's the direction of the angular velocity? What's the direction of L and omega? Okay, it should be pointing to the left. Because you see, as I spin the boomerang like this, spins this way, right hand grip rule, it points towards my ear. Now another piece of the puzzle is actually what happens to the boomerang when it spins. If you really think about the boomerang, if it is moving forward like this, and it's spinning at the same time, right, moving forward and spinning, what this actually means is that the top blade is moving much faster because it's moving forward and spinning. Whereas the bottom blade, you look, it's actually spinning backwards while the whole boomerang is moving forward. So the speed, the real speed of this blade is actually much lower than the speed of the top blade. This also means that the lift forces, the aerodynamic forces that the boomerang experiences are much larger at the top here than at the bottom. So as the boomerang spins, right, the top part experiences a larger force than the bottom part. And so there's a tendency for the boomerang to turn this way, right, to turn inwards. Now if you think back to your right hand grip rule again, this turning effect, this torque, right, turning effect is actually torque. This turning effect causes the boomerang to spin this way, and so if I put my fingers this way, right, turning this way, the torque is actually pointing behind me. I will draw that on this top view diagram. See, the angular momentum is to the left, and the torque is pointing behind me. So what is torque? Remember, torque is the rate of change of angular momentum, dl dt. So torque changes angular momentum. When I just release the boomerang, the angular momentum is pointing this way, right, at time 0. The torque backwards will cause this angular momentum to change. So I add these two vectors at the next instant in time. The resultant, right, this new angular momentum would actually be pointing somewhat backwards. So if you visualize this, what's happening is that at the next instant, the boomerang is tilted to the left, and the angular momentum is, because the angular momentum is pointing this way. So repeating this argument, we will see that the boomerang will go in a circle and come back to us. So we've just shown that the spinning motion of the boomerang, right? This particular spin plus motion, this effect actually causes a torque, which then causes the angular momentum, the L vector, to do what we call precession, meaning to go round in a circle, okay, to turn round. And this really is the explanation for why the boomerang comes back to you. Now, I want to leave you with a little challenge problem so you can work on it. What do you think will happen if, let's say, I use some glue tack or some adhesive putty and stick it to the blades of the boomerang, just a little bit. If I stick an equal mass on all three sides, this will increase the moment of inertia of my boomerang. Now, what do you think will happen when I throw the boomerang? Wasn't that a fun problem to think about? Did you manage to figure out that the boomerang with the added masses will actually go in a larger circle than before? What we said is we keep omega constant, right? We keep omega unchanged. But we added the masses, so the moment of inertia is greater, right? This means that, therefore, the angular momentum will have increased, since L equals to I omega. What about tau? What about the torque? Well, we know that torque is dl dt. That's the equation number 2 over there. And if you think about it, actually this is unchanged. This is also constant. Because what we said is that the boomerang will spin in the same way as before, right? Same omega. But the only difference being that the I has increased. Well, the air doesn't know that, so the forces don't know that. The lift force will be the same, and so the torque acting on the boomerang is the same. Does this mean that the circle is unchanged? No, quite the contrary. See, in the initial case, we have our angular momentum of the boomerang pointing to the left. With the blue tack, the angular momentum is now larger, right? But the torque is the same. That means in the same time, there's the same change in the angular momentum. So when we add this, when we do this same argument, right, to change the delta L, the length of this blue arrow and the length of this blue arrow should be the same. This delta L should be the same. So because these delta L's are the same, when I have my resultant, we see that this angle here, the original angle theta, as compared to this angle where you add the mass, theta will be larger than theta prime. Meaning to say that in the original case, the boomerang will fly in a smaller circle because it will turn faster. Okay, so in the case without the masses, the circle might be something like this. With the masses added on, the circle will be something like this. And this is something that we can see in real life as well. You should try it out. Okay, the boomerang goes much further before coming back. Okay, it doesn't come back quite exactly to my hand, but it still goes further. I'm sure you'll agree with me that it takes time and effort to understand such theories. After all, science is not built in a day, and scientists and mathematicians have been doing research and experiments, lots of thinking and dreaming to come up with such theories. And I'm sure you have lots of time to think about such things further when you play your boomerangs at home. Now, the concept of precession is actually applied in gyroscopes, and we actually use these concepts in applications such as navigation for aircraft and ships, as well as if you observe what happens to a top when it spins around the table, you'll notice that there's actually some precession going on. At this point, I'd like to invite my two assistants, Don and Minghui, to actually demonstrate to us today, the wonderful science of precession and what wonders it can create. As you can see, they are holding on to the samurai sword, and suspended from it is a bicycle wheel. The bicycle wheel is attached by two strings to the sword. And what I'm going to do now is actually to spin the wheel and cut one of the strings. Right, amazing as that might sound, I'm going to just do it. Spin the wheel. There. Isn't it amazing how the wheel doesn't fall? But really, it's just like the boomerang. See, this wheel is spinning so fast, it's got a high angular momentum. So the torque due to gravity causes it to precess rather than to fall. Hey, thank you to my two assistants, Minghui and Don. I hope that today you've had fun learning about how to make a boomerang and to understand the physics of a boomerang. And I hope that I've got you started thinking on this bizarre notion of precession of angular momentum. To end off, I'd just like to say that as the science samurai, what I do is not magic. My power comes from the wonders of science. Hi, this is a note for the teachers, and I am so glad that you are considering using this Blossoms module in your lessons. The focus of this lesson is to encourage hands-on exploration of physics, and not just the theoretical kind of laws and equations. And we hope that this can really inspire students to be interested and excited about science, because I think the attitude is much more important than all the actual concepts and theories introduced. We provide some links to resources, additional resources, and you can further explore these links on the website. Okay, in terms of prerequisites, I think all students can take away something meaningful from the lesson regardless of their background. But for the lesson to work best, I think they would need three things. Number one, basic understanding of forces and vectors. Number two, the understanding of Newton's laws, F equals ma, dp, dt, that kind of thing. And number three, basic time derivatives and vector addition. Okay, these are the three main things that the students would need to know. Okay, I have deliberately kept the discussion more qualitative rather than quantitative, because actually the actual movement of the boomerang is much more complex than I've made it sound. The materials, right? I'm not sure if you would have difficulties getting them. They're quite straightforward. So there's stapler, pencil, ruler. I think the hardest part is the cardboard. I think for this, you really have to just try to experiment a bit with different kinds of cardboard. What works best is actually something rather stiff, yet still being somewhat flexible. Okay, these kinds of material have the best performance. And I strongly advise that you do try making your own boomerangs before class, because students will definitely ask you for troubleshooting advice and tips during your lesson. Okay, there's one thing that would be nice if you had. I don't have one with me right now, but if you had a gyroscope, you could actually bring that to class. That could be a possible extension to the lesson. Now I'll run through just some of the suggested activities for each of the segments, for the breaks after each of the segments. Okay, after segment 1 is for the students to construct the boomerang, so just help them out with this. You might want to replay the video so that students can dwell a bit longer on some of the steps.